from the 4th, 5th century. It's an ocean-going ship. We know that. There are no oars along the edge, so that's quite obvious. There are other depictions as well, which we have used. There are surviving boat-building traditions that are there. There are obviously the Omani reconstructions, and of course we have done a lot of in-house research on ancient texts, etc., including the Yukti Kalpataru. And you can see this sort of sketch over there. What does such a ship would have looked like? It has 3 masts in the middle, and it has a foresail as well. And as I said, it uses these 2 trailing oars to do the ruddering. It doesn't have a rudder as we know it today. So we have converted this into a concept design. So this is the ship we are actually going to build. Given the sort of size and scale, we have reduced the number of masts to 2 because that would allow more space for walking around and so on. It was just getting too cluttered. It will have 2 main masts, and then we will retain the foresail. You can see how it looks from both the top and from the front. We have retained also the trailing oar. Now this is something that we will have to really experiment with when we are testing the ship, because we actually don't know the sailing characteristics of a trailing oar as the rudder, rather than the rudder, the type of rudders we use, the central single rudder that we have got used to using in modern times. Importantly, we will also be using square sails, not lantern sails. Again, the triangular lantern sails that are very often used today for most sailing. Lantern sails, by the way, are also ancient and are very likely an Indian invention. So it would not have been wrong to use a lantern sail in our reconstruction. But we are using a ship from a period where these lantern sails were clearly not used. So we have to be true to the period. And since they seem to be using square sails, we will be using square sails. Square sails do rather well if you're sailing with the wind, because it has, it's a square, large surface area. But then if you have to sail at some angle to the wind, it causes, it's less efficient. So what are the principal dimensions of the ship? So the length we are attempting is 21 meters. The breadth is 6.5 meters. So we are not quite going with the dimensions that in the Yukti Kalpataru. Then the depth of 4 meters, and the propulsion will be, as I said, 2 main sails and 1 foresail, all square size. And the crew will be 1 captain plus 12. This is the development of the line plans. There are all kinds of pressures and frictions and other things that a ship of any kind faces. So there you have on the zone 1, that's the potential flow, that's all the pressures that come in from the waves and other wider movements of water. Then there is the zone 2, which is the thin boundary layer. That's the immediate skin friction of the ship that's happening against the hull of the fluid movement. Then there is zone 3, which is the viscous flow, which is happening, the wake, the viscous pressures, resistance, and so on. So these are the kinds of things that we need to think about when we are designing the ship and trying to get a sense of what is its efficiency. The Navier-Stokes equations basically deal with the fluid flow around the ship's hull, which are represented here by both the conservation of mass and the momentum equations. The basic idea here is to get a sense of the sense of the viscous forces, the body forces, the pressure forces that this ship's hull will face, particularly given that it is a kind of hull that we are not usually used to. So we had to model this. So here is the fluid ship interaction. I won't get into the details, but basically we want a sense of the forces on the hull. And remember, there are 6 directions in which these forces are applying. There's the forward, backward direction, there's a sideways direction, and there's the up and down direction. Those are the 3 linear directions, and then there are the rotational directions, also the equivalent in 3 different directions. So there are the 6 forces. And then we have the viscous force, which is the frictional drag. You have the pressure force, which is the form drag, the forces due to the ship's motion, forces due to the wave excitation. And then there's the hydrostatic or body forces, gravity, and so on. So using these Navier-Stokes equations, we have done a 3D model of the hull form. So this is just so that you get a sense of that, what the hull form looks like. And then this is then, these equations are then applied to this form using the computational fluid dynamics modeling. Many of you, again, are maybe very familiar with this, all of this. And then these Navier-Stokes equations are solved not just for the whole, but actually by meshing, you do it for every little bit. So then we get the free surface wave pattern for this. This is a very basic, and you get the streamlines and the resistance simulation. But as I said, we need to be very clear that the surface of the hull that we are simulating is smooth. And this is very different from the roughness that we are going to get because of all the external stitches that we are going to use. And of course, remember, even the planks are not exactly entirely smooth. That would have with, say, a metal or any other kind of, or fiberglass surface. And then you have to test it through hydrodynamic testing in a towing tank. So we have to build a model and you have to tow it. We will do one through in a wave basin, which I think IIT Madras has one of these towing tanks. So we were going to test it there. Now comes the building of the replica. As you can see, a replica has been attempted. And this is a first cut glimpse of what this ship would look like.